Okay, good evening, everyone. So today we start with the live session for the content of week 10 on this NPTEL course on hydraulic engineering. And basically, this particular week was devoted to the discussion of the basic concepts of viscous fluid flow. Viscous fluid flow. So this was the concept. So as usual, before moving to the practice problem, we will discuss some very fundamental concepts that was already discussed, that you have already seen if you have already gone through the lectures. So let's begin. So the most important concept that you should give stress for this particular week's lecture is the deformation. It is the deformation of a fluid element. Now, how a fluid element can deform? Okay, so what are the different modes by which a fluid element can deform and how you can quantify this deformation? Okay, so the deformations can be broadly classified into four parts. Okay, so number one is translation. Okay, translation. Then number two is uh, linear deformation. Sorry, number two is linear deformation. Then number three is angular deformation. Angular deformation, and then number four is rotation. So these are the modes of deformation of fluid element. So if fluid element can, means, when do you say that the fluid element has deformed? When there is a translation or linear deformation, angular deformation, or rotation. Okay, so what exactly are these? So the translation is basically when, without any change in the length of the fluid element in any direction, it is simply moving, it is simply changing its position. Say it is moving from position 1 to position 2, or say position P to position Q. Okay, so this simple movement without any deformation or without any change in length along any of the direction is termed as translation. Okay, so translation along x, y, and z direction. If suppose you have a fluid element whose velocity field in the, or the flow field is u I cap p j cap plus w k cap. Okay, so if these three are there, then the translation along x direction is u dt, where dt u dt is what? Use the velocity, dt is the time interval. So this velocity into time is giving you the displacement, or it is basically a distance the fluid element is moved along x direction. Similarly, translation along y direction is v dt, and along z direction is w dt. Okay, so this is translation. Then second is linear deformation. So what is linear deformation? Linear deformation is, say, change in the length. Okay, it can be considered as the linear deformation. The linear deformation can be considered as the change in the length in each direction. Okay, change in the length in each direction, that is x direction, y direction, and z direction. Okay, so the change in the length in each direction is, sorry, change in the length in each direction is termed as the linear deformation. So if you have gone through the lecture, see there is like I will not go into the derivation of these different deformations because it has already been discussed in very much details in the uh, lectures of week 11. No, sorry, lectures of week 10. It has been discussed in too much details, in-depth details in the lecture content of week 10. Therefore, I will not discuss. We will not discuss the details of the derivation, but we'll simply try to go through rapidly to these very important concepts. Okay. So linear deformation is basically given by, so it is basically what? Change in the length in each direction. So change in the length in each direction. So along x direction it is, sorry, along x direction it is del u by del x into dx into dt. Okay. Del u del x dx into dt, then del v del y dy dt along y direction, and along z direction del w del z dz dt. Okay, so these are the components of linear deformation of a fluid element along x, y and z direction. So what exactly is this? See, our fluid element is something like this, a box, okay, something like this. This is our fluid element, such that the length along x, y and z direction are dx, dy and dz. Okay, now what does this basically represent? Okay, what does this represent? This translation represents the distance traveled by a fluid element in the time dt. Okay, this represents change in velocity. Okay, this represents change in velocity in a particular direction multiplied with time. Okay, so del v suppose into dt. Okay, so this is represented by, so del v or change in velocity along x direction is del u del x dx, along y direction is del v del y into dy, and along z direction is del w del z into dz. So this is linear deformation. Then we have, see, you consider this same fluid element. Okay, you consider this same fluid element, and if suppose there is linear deformation along all the three direction, that is x direction, y direction and z direction. Okay, so if it is deforming, linearly deforming, if this particular fluid element is linearly deforming along x, y and z direction, what does it signify? It signifies that there is a change in the volume of the fluid element. Okay, because change in the volume, okay, because this is changing, this dx is changing, dy is changing, dz is changing. Okay, so so the rate of volumetric change or volumetric strain is given by what? It is given by del u del x plus del v del y plus del w del z. Okay, so what is this? This is nothing but the divergence of the velocity field. So the divergence of velocity field physically represents the rate of volumetric strain. Okay, rate of change of volume or rate of volumetric strain, rate of change of volume of a fluid element is represented by divergence of velocity. Okay, now for an incompressible fluid, okay, for an incompressible fluid, the continuity equation reduces to the divergence of velocity equal to 0. So see, the word incompressible means that you have something which cannot be compressed. Now since you have something which cannot be compressed, it simply mean that there is no volumetric strain. Okay, now the next type of deformation is the angular deformation. The next type of deformation is the angular deformation. So angular deformation is basically what? Angular deformation is the difference. Okay, it is the difference between the angular difference between the angular deformations of the individual sides delta x, delta y, delta z of the fluid element. Okay, so how can you get this angular deformation? See, angular deformations usually represented by, see, if you take these two, so they are basically a symmetric matrix, or half of del v del x plus del u del y. Similarly, if you take y z, this will be equal to zy half of del w del y plus del v del z. Okay. Del w del y plus del v del z, and similarly we have epsilon zx equal to xz. Okay, so it will be half of del w del x plus del u del z. Okay, so this is the angular deformation. Okay. Then the rotation. So rotation, as we have seen, the rotation, average of the rotations of the sides. Okay, suppose you are considering, say, in pairs. Okay, say you have considered the side dx dy. Okay, then you have considered the sides dy dz, then you have considered the side dz and dx. Okay, so the rotation is the average rotations of the sides dx dy, dx. Okay, now how basically it is calculated. Suppose you are calculating the rotation for the xy plane. So it is, if something is rotating, say this particular element is rotating on the xy plane. Okay, so basically the axis of rotation will be the axis which is perpendicular to this place, so basically the z axis. Okay, and it is given by half of del zx, okay, minus del y. There is a technique basically how you can write it. See, z, if you write it in a sort of cyclic way, x y z y z x z x y. Okay, so z x y, so you can see z x y. With x you write v, with y you write u. Just reverse the velocity field. Okay, so this is for the xy plane. Similarly, you have omega y and omega z, and overall you have a omega vector, which is half of basically curl of the velocity field. And if you remove this half, whatever you are left with is the vorticity. Okay, it is the vorticity. So this is a very important concept, and the rest is the derivation of the Navier-Stokes equation. Okay, derivation of the Navier-Stokes equation based on Stokes hypothesis. Again, I am not going into the details of the derivation because it has been covered with great clarity in the lecture videos provided by Professor Muhammad Saud Afzal in the lecture videos of week 10, the NPTEL course. So we will straightway move to the problem solving part. Okay, now for the problem solving part, see, the problems that are basically there in this particular module or week are very simple. Okay, so for the following flows you have to determine the components of rotation about the various axes. Okay, so u v w, that is the flow field, is given for three different cases, and you have to determine the components of rotation about the various axes. Basically for all these cases you have to determine the value of omega vector, that is omega x, omega y and omega z for all these three cases. Okay, so it is a very simple case just now we have seen. So please try this problem. Okay, and then we'll discuss the solution. So it is a very simple problem. So the components, as I have just discussed, omega z, omega x, omega y. So for the first part, u is xy cube z, v is minus y square z square, w is yz square minus half of y cube z square. So omega z is half of del v del x minus del u del y. So you basically find the partial derivative of v with respect to x, which is 0, and then you find partial derivative of u with respect to y, which is 3xy square z. Okay, so this is omega z. Similarly, you find omega x, omega y, and you'll be, so that is the answer. Similarly, for problem 2, you do the same exercise and you find. Okay, now, in case of problem 2, it is basically only U and V, and for problem 3 also U and V are given. So, it is basically a two-dimensional flow field. So, if it is a two-dimensional flow field, okay, so X and Y is only there. So, there will be only omega Z. Okay, there will be only omega Z. Huh? There will be no omega X and omega Y. Okay. And in the second part, you can see that only omega Z is there, and that to the value is 0. So, it basically represents a case of a rotational flow. Okay. Then, show that in an invisible rotational flow, the streamlines and equipotential lines cross each other at right angles. Now, this is a very important problem. See, for a streamline, okay, for a streamline, the stream function psi along that streamline is constant. Now, d psi can be written as del psi del x dx plus del psi del y dy. Okay. Now, slope of this streamline dy by dx for a constant psi is d psi by dx del psi by dy. Then from basic definition it is minus v by u. Similarly, for a potential function, d phi is del phi del x dx plus del phi del y dy for a two-dimensional flow. And the slope of this equipotential line m2 is dy dx phi constant del phi del x by del phi del y. So del phi del x is u, del phi del y is v. Now, if you multiply the slope of these two lines, you are getting a value of minus 1. So, if you if you just try to revise, or you try to remember the concepts of coordinate geometry, when there are two lines, and if this the slope of these two lines are multiplied with each other, and if it gives a value of minus 1, it simply signifies that there is a very simple proof also, okay, that these two lines are perpendicular to each other. So basically, in a flow net where the potential lines and the streamlines cross each other, at the point of crossing means they always intersect each other at 90 degrees. They are orthogonal. Okay. Then one more exercise I'm leaving for you. Okay, it's a very simple problem. See, we have already obtained the value of rotation for these three. That is the first problem. Okay. Now suppose you have to obtain the vorticity for all these three subparts of problem 1. What will you do? So what is vorticity? Vorticity is basically del cross V. Okay. Del cross V. So if you multiply 2 with the omega, that is rotation, you will be getting vorticity. So please calculate the vorticity. Okay. So that's all for today's session. If you have any doubt, you can ask, or otherwise we'll stop and again meet next week, same time. Any doubt? Okay. Seems that there is no doubt, so we can stop here. Thank you.